Right. So we are discussing chemical bonding. Welcome to the session again. There are two things why we are introducing the concept of hybridization. If you can understand properly, then I think you will understand the entire concept of what hybridization, right? It all started off with ionic bonds, and we were very convincingly explaining the concept of ionic bonding. And it was so convincing, I say, because you have oppositely charged ions, a cation and an anion, and they're existing strong electrostatic forces of attraction. The strength of the ionic bond is derived from that strong electrostatic forces of attraction that prevails between an anion and a cation, and everyone are convinced. And if there is any bond which is deriving strength by default, it's nothing but what ionic bonding, at least for the explanation purpose. Right? It's very easy to understand where the strength of the ionic bond comes from, because an electrostatic force is a strong force, and that will be existing between oppositely charged ions. And of course, it is existing between an anion and a cation in an ionic bond, and everyone understands the strength is derived from what? That particular force, that is a strong electrostatic force, that is referred to an ionic bond. It is as simple as that. But coming to the covalent bond, we always have issue. Like, for example, why people go for sharing of electrons, right? It was told in our school that, the atoms don't have octet. The atoms do not have octet. So in order to get that octet configuration of the noble gases, they try and share the electrons. And in the process of sharing, they are not losing electrons. You just invest it. And the invested electrons doesn't come out of the shell of that particular atom. It is just invested. Similarly, other atom invests, and the invested pair, what we call it to be a bonded pair, is put at the center, and it's counted for the octet for both the atoms which are participating in covalent bonding. This is what our teachers told, and this is what is the perception we have developed from the school when we started reading covalent bonding, right? All this is fine, but one question if we ask, where does the strength of the covalent bond coming from? Where does the strength of the covalent bond coming from? Then I think this explanation of yours, that you invest one electron, I invest one electron, and both are sharing to achieve octet, seem to be not at all convincing, because the question will be asked repeatedly, where does the strength of the covalent bond coming from? What is that which is holding these two together? What is that which is holding these two atoms together is a question which will be repeatedly asked, even though you're telling that we have invested electrons and the pair of electrons is counted for both the atoms for the octet, and all these things you will be telling. But remember, nothing is convincing to explain where does the strength of the covalent bond come from. So these are the issues which we have tackled by proposing the concept of what? Overlapping. Well, that is the main concept, the concept of overlapping, what we have introduced in the valence bond theory proposed by Linus Pauling. In the concept of overlapping, when we introduce the concept of overlapping, it is introduced only for single purpose, to tell people where does the strength of the covalent bond comes from. So the concept of overlapping will be explaining to you where does the strength of the covalent bond come from. That is the only purpose. And remember, it was explained beautifully. Of course, the concept of overlapping is a feat to explain the strength of the covalent bond, because the very first postulate, what Linus Pauling says, is the strength of the covalent bond is derived by overlapping of atomic orbitals. So basically, a covalent bond is formed by overlapping of atomic orbitals. So he, for the first time, is introducing what? The concept of overlapping. You must understand. What happens in overlapping is simple. First of all, you divorce the thinking that, two atoms are overlapping with one another. It doesn't happen like that. The atomic orbitals in one particular atom, the atomic orbitals in another particular atom, the orbitals actually overlap, and there are conditions for the orbitals to be overlapping. Not every orbital will be overlapping, only those orbitals in which the electrons possess opposite spin shall be doing this. So, for example, if you take chlorine atom, you have 3p-Z electrons which have unpaired electrons. So even though the chlorine atom is big, the chlorine atom is not overlapping with the other chlorine atom. It is only the 3p-Z electron in the chlorine atom and the 3p-Z of the orbital of the other chlorine atom, they are overlapping. and they are holding this chlorine and this chlorine together. That's how the bond is formed. So in the overlapping process, what is happening? Where does the strength come from? You must understand that it comes from, because overlapping, what you're doing is when two atomic orbitals are overlapping, then they delocalized over a larger volume, meaning simply the electron is now able to move around on a larger volume. Earlier you're restricted only to one atom. Now you have two orbitals coming together, and thereby the electron has larger volume to actually roam around. When you move around a larger volume, you will be losing energy, and thereby you gain what? Stability, you must understand. Right? This is what is the thing. So the concept of overlapping is the one thing in Linus Pauling you can take home. Right? So the concept of overlapping is basically telling you where the strength of the covalent bond is coming from. Keep that in mind. Second, even though Linus Pauling was explaining greatly, beautifully rather, diatomic molecules like HCl, and you have hydrogen, you have chlorine, you have several other atoms, he was beautifully explaining all these atoms. Right? But the issue is, when it comes to polyatomic molecules, then 3 or more atoms are involved. When 3 or more atoms are involved, then understand that the bond angle kicks in. Because for explaining the bond angle, you require minimum 3 atoms, right? So till diatomic molecules, everything was beautiful for Linus Pauling. When it comes to polyatomic molecules, there is an issue. And I was actually highlighting 2 of the biggest drawbacks of Linus Pauling, which made the basis for us to introduce the concept of what? Hybridization. One, the projection of p orbital onto s is not fixed. So whenever you will see a p orbital which has a direction is projected onto the s orbital, the direction is not fixed, meaning whether it comes through obtuse, perpendicular or linear is absolutely not fixed, that too at the nick of the moment. That is the biggest issue. That is one of the biggest drawbacks of what? Valence bond theory, that the projection of p onto s is absolutely not fixed. So what happens? The bond angles are not fixed, the shapes are not fixed. So we face problems when it is polyatomic molecules. The Linus Pauling's theory of valence bond theory could not actually explain all these molecules. It is fantastic as far as diatomic molecules is concerned, but polyatomic, it not only fails but miserably fails. One more thing which is absolutely silly and ridiculous is basically, he says whenever the p orbitals are involved in bonding, the bond angle remains to be 90 degrees, which is further silly and ridiculous for me. Because if that is the case, then all the 6th group hydrides and all the 5th group hydrides, he's basically telling me that ammonia, PH3, water, H2S all have the bond angles equal to 90 degrees. All equal to 90, which should not be the case. It is actually silly. Because ammonia is 107. If you call Linus Pauling and ask him, wow, the bond angle is 107, could you please explain? He's not in a position to explain. Hence, it is a serious drawback, not a silly drawback, which cannot be discounted. Of course, it is a great drawback. You must understand that. So, these 2 are forming the basis for the concept of hybridization. So, why I'm introducing hybridization is, we don't wait till the overlapping thing. What we are doing is, I draw the attention. In hybridization, 2-3 things are important. Number 1, it all happens before bonding. Where it happens? In an atom. So the atom, before bonding itself, the hybridization takes place. Remember, before bonding, the atoms have still not participated in bonding. Before bonding itself, the hybridization is taking place. Why before bonding everything must take place? Because to avoid that last minute thing that from where, which orbital, the projection of p onto s is not fixed, from where I should come and all this. So the aim of hybridization is basically to produce better directional orbitals. To produce better directional orbitals. These are called the hybrid orbitals. You must understand. So basically he is telling that the hybrid orbitals have better directional properties than your atomic orbitals. So basically in our language, in the simplest of the language, what we are doing is, before bonding itself, everything is fixed. The orbitals are sitting in a position, the bond angle is fixed, then you are inviting the partner for coming off or overlapping. That is the idea. That is the basic idea. Before bonding itself, the orbitals are sitting in a position. Position means in a particular bond angle, so the bond angle is fixed, structure is fixed, everything is fixed. Then the strange thing is before bonding. You must understand. So what does the concept of hybridization give us technically is to produce better directional orbitals. Better directional orbitals, that is nothing but what? The hybrid orbitals. So simply speaking, hybrid orbitals have better directional properties compared to what? Your atomic orbitals, you must understand. Right? And in the process, I was telling you, what is hybridization is basically the intermixing, right? The intermixing of atomic orbitals within the atom before bonding. So the intermixing of atomic orbitals, that is s, p, d, f, within the atom before bonding in excited state to generate more directional orbitals, that is nothing but hybrid orbitals, is called what? Hybridization, you must understand. So everything is hypothetical. We are just catering to explain bond angles of certain molecules which are already formed. Hybridization is no method of preparation for those molecules. The molecules are already existing. We are just trying to give a convincing theory why the bond angle is so much, why the shape is that much, why the structure is that much, structure is formed like that, all this. But a hybridization is no method of preparation for molecules, you must understand. So I call it hypothetical. So what is hybridization? It is hypothetical intermixing of atomic orbitals in the atom before bonding to generate entire new set of orbitals that are called hybrid orbitals with better directional properties. So I have ensured I am ready before bonding, before calling my partner. I am ensuring, right? So if I look into the intermixing, this is 1s, 1p, 2p, and 3p. So it's basically, you see 1s and 3p orbitals give 4 sp3 hybrid orbitals. This I was explaining you in the last session. So you said intermixing of atomic orbitals, right? You said intermixing of atomic orbitals. Yes, it is intermixing of atomic orbitals within the atom before bonding, before I call my partner. It's all hypothetical, right? So 1s and 3p's, the intermix giving you 4 sp3s, 1 sp3, 2 sp3, 3 sp3, 4 sp3s. And each sp3 will be having characteristics of s as well as p. How much characteristics depends on how much you invested. It's only one S, right? So you'll have 25% S character and 75% P character. So one of the sp3 hybrid orbitals looks more as what? P, less as S. So if you see the 4 sp3 hybrid orbitals, they look like this. Now what are these? Is sp3, this is sp3, this is sp3, and this is sp3. Remember that. And this is what an atom is doing before inviting the partner for bonding. So understand hybridization. It's basically intermixing of atomic orbitals, say like this, right? Intermixing of atomic orbitals and sit in positions. Right? All this is happening before bonding, such that to avoid that last minute questions what you have asked earlier in Pauling's theory, that I need to come obtuse or perpendicular, p orbital projection of s onto s is not fixed and all these things, right? So this is how it is, and it has now the bond angle is 109 degrees 28 minutes. You must understand. It's basically 109 degrees 28 minutes, right? It's 109 degrees 28 minutes. You must understand that. So it has a better directional properties. So it's not necessarily intermixing of 1s and 3p's. You can have 1s and 2p's. You have 1s and what? 1p. You can have 1s and 3p's and 1d. It extends to d also. You can have 1s and 3p's and 1d, right? So it extends like that. So if I can give you a list of all this, Just as a quick recap such that we can move forward, watch carefully here. Look into this. If you have 1s, 1s and 1p, then you will get 2 sps. The bond angle is 180 degrees and the shape is linear. And the shape is linear. You can have 1s combining with 1s, 1p. Then you get 2 sp what? Hybrid orbitals. You must understand. Right? And you can have 1s and you have 2p's. Then you get 3 sp2 hybrid orbitals. And then the bond angle is 120 degrees and it is triangular planar. It's triangular planar. Similarly, you can have 1s and 3p's. Then you get 4 sp3 hybrid orbitals where the bond angle remains to be 109 degrees 28 minutes and the shape is tetrahedral. So you can have an intermixing of 1s and 1p, or you can have an intersection of 1s and 2p's, or you can have a 1s and what? 3p's. All this intermixing of atomic orbitals are happening within the atom. Within the atom, that too before bonding. In excited state, I sit in a position and then call the partner. So you are basically ready for bonding first. You're basically ready for bonding first, sitting in a certain positions and then call the partner. Then I think the structure is fixed, the bond angle is fixed, everything is fixed. You must understand, right? And let me get into some of the examples and beautifully explain all these sp3s, sp2 and sp. But before that, we have issues. Like, a student who wanted to write the exam wanted to know few things. I give ammonia, I give water, I give methane, right? And to know which type of hybridization takes place. For example, this is the nitrogen in which hybridization is taking place. Here it is oxygen, here it is carbon. So 3 compounds are given to you. And I wanted to know in which atom, which hybridization is taking place. Because as I said, the intermixing of atomic orbitals, so it can be 1s1p, 1s2p's, 1s3p's. Which type of hybridization shall be taking place in these molecules, which we need to discuss that. How do we know? How do we know in advance? That is for the student who is writing the exam. So if you're given n number of compounds, even I continue to write SO3, SO4 minus 2, SO2, SO3 minus 2, XCF2, XCF4, XCO3. You have n number of compounds. How do we know which type of hybridization is taking place in a particular atom? Then it is an important question for the students who are writing the exam. Most of them will be cleared if you know what is the hybridization in this, right? Because the chance of 1s and 1p, the chance of 1s and 2p's, the chance of 1s and 3p's are very much existing. And it all depends on which molecule you are actually taking. For the student who is writing the exam, how can he judge which type of hybridization is taking place in these compounds? That will be the point of discussion today. So let me propose a formula to you such that you will be in a position to answer the type of hybridization that a central atom will be having in a particular what species, right? Here is the formula. Observe carefully now. So look here. To judge the type of hybridization hybridization in a particular species, radical or a molecule, right? To judge the type of hybridization that takes place in a molecule or even a radical, you must understand. To judge the type of hybridization in a molecule or in a radical in the sense a positively charged species or a negatively charged species. So I draw the attention. You have n number of compounds and you have to name the hybridization that takes place in that particular species or radical. because the chances of intermixing of atomic orbitals are very high. The permutations and combinations are very high. So how will a student know what type of hybridization is taking place in that particular compounds is a point of discussion you must understand. So I give the formula first. This is the formula to calculate. H is equal to half into V plus M minus C plus A. That is the formula which is used to calculate the type of hybridization that is taking place in a particular species. So if I ask you what is hybridization in boron in BCl3 molecule, or I can ask you what is the hybridization of oxygen in water molecules, what is the hybridization of carbon in methane? So these are the questions. If you know the type of hybridization, then I think we can frame the theory. So hybridization is a convincing theory, so you should be knowing what type of hybridization is taking place in a particular species, and hence I propose the formula H is equal to half into V plus M minus C plus A. Now let us understand what is H, what is V, what is M, what is C, what is A. Right? So what is H? H is number of hybrid orbitals generated. Number of hybrid orbitals generated is H. Is H. Now what do you mean by this? As I said, if you look into 1s and 3p's, if they have intermixed, 1s and 3p's, 1s and 3p's, so it will be total 4 sp3s. 4 sp3 what? Hybrid orbitals. So if you have 1 Cadbury, 3 neutrons, you will get total 4 chocolates, which will have the taste of Cadbury as well as what? Neutrons. You must understand that. Right? So the number of hybrid orbitals generated is equal to the number of atomic orbitals involved in hybridization. You must understand. So if you wanted to know the number of hybrid orbitals, then you should know the number of atomic orbitals involved. Suppose it is 1s and 1p, only 2 atomic orbitals involved, so you get 2 hybrid orbitals. If 4 atomic orbitals are involved, you get 4 hybrid orbitals. If 3 are involved, 3 you will get it. 5 are involved, 5 you will get it. But how many are involved? Right, for that I have a formula. But whatever, H is nothing but the number of hybrid orbitals generated. Now what is V? What is V? Well, V is the number of valence electrons in the central atom. Now, what is central atom? The central atom is that in which hybridization is taking place. The central atom is that where the intermixing of atomic orbitals are taking place. That is called the central atom. Must understand this. Right? So, H is nothing but the number of hybrid orbitals generated. Number of hybrid orbitals generated. What is V? The number of valence electrons that are present in what? The central atom. Now, to make it simple, V is not valency. Mind you, you cannot be casual. V is not valency, please. V is not valency. It is the number of valence electrons that are present in the outermost shell of a central atom in which the hybridizations are taking place. So otherwise, I'll make it simple. Number of valence electrons, or otherwise this can be also called group number. It's a group number because group number is nothing but the number of valence electrons you have. For example, carbon has 4 electrons in the outermost shell, that is valence electrons. So it belongs to 4th group. Boron has 3 electrons in the valency shell, so it belongs to 3rd group. Nitrogen has 5, so it belongs to 5th group. Oxygen has 6, it belongs to the 6th group. Halogens have 7, hence they belong to the 7th group. Either of the things you should know. Either you should know the number of valence electrons that are present in the central atom, that is the number of outermost electrons, or at least you should know the group number of that central atom. So V is not valency. Valency is a combining capacity of an element. Don't mix it up with this. V is the number of valence electrons that are present in the central atom where the hybridization is taking place. Must understand. So otherwise it is called group number. Then coming to C. What is C? C is the cationic charge. The cationic charge. As I said, what are we doing is judge the type of hybridization in a molecule or a radical. Now radical is the one which possesses charges. It is a cation or an anion, whatever. The one which bears positive charge, the one which bears a negative charge. So what is C basically is the charge on the cation. And mind you, it is only the charge which you need to put it, not the sign. For example, the charge on silver, if someone is asking, it is 1. Don't write +1. Plus and minus are adjusted over there. The charge is a scalar thing which you need to write only what? The number. Like for example, if I write sulfate ion here, the charge on this is 2. The charge on the anion is 2, right? Don't write -2. I need only the charge, not the sign, please. Right? The charge on say CH3 plus, the charge is only 1, not +1. Don't write that. Right? You need to put only the charge and not the sign. So C is cationic charge, only charge please. And A is again anionic charge. Anionic charge. Suppose if this is the anion, the charge on this is 2. Don't put -2, it goes wrong. I need only the charge to be mentioned in the formula, not the sign. So let us take examples for making things easy. Right? I'm telling you what I'm doing. Let me be very clear. I put it in sequence. First of all this discussion has started because there are issues in the valence bond theory. Now, what are the issues in the valence bond theory? Number one, projections of p orbitals onto S, the angle in which the p orbital overlaps with the S is not fixed. It is obtuse, perpendicular, linear, whatever is not fixed. If it is not fixed, bond angles are not fixed, structures are not fixed. That is a major issue. Second thing is, whenever p orbitals are involved in bonding, the bond angle remains to be 90. That means that H2S has 90, water has 90, ammonia has 90, PH3 has 90, every fellow has 90, which is ridiculous, meaningless, nonsense, nuisance. So these two are the key points which I am proposing and forms the basis for what? Hybridization. So in hybridization, we are generating an orbitals which have better directional properties, indicating that before bonding itself, everything comes fixed. Everything is fixed. Bonding is still pending. Before bonding itself, within the atom, which I am referring it to the central atom, which I am referring that to be the central atom. The hybridization takes place. The hybrid orbitals are sitting in an angle. Bond angle is fixed. Everything is fixed. I am ready. For what? Bonding. Then I clap and call my partner for overlapping. That is the concept of what? Hybridization. The key takeaway of all this, what I'm telling is, all this is happening before bonding. At the time of bonding, no questions which way to come. Shall I come from obtuse? Shall I come from acute? Shall I come at 90 degrees? All these questions are completely out now in the concept of hybridization because I'm sitting in positions, you must understand. Got my point? And the other question arises, that is the beauty of hybridization. And the other question which people will ask me is, you have hundreds of species, hundreds of molecules, which hybridization takes place in which atoms? Can you make it simple? Yes, I have made it simple for you. How is that? Look into this. H is equal to half into V plus M minus C plus A is the formula which you need to use when to judge hybridization in a particular molecule or a radical, right? For example, say this. What is H? Number of hybrid orbitals generated. If you can know the value of H, we can judge the hybridization in it. But the issue is how to determine H. How to determine H? For that, You need to know the group number of the central atom, that is the valence electrons, right? And I didn't write M. What is M? What is M basically? We didn't write M. M is number of monovalent atoms attached to central atom. M is the number of monovalent atoms that are attached to the central atom. Don't get threatened. Number of monovalent atoms in chemistry are only hydrogens and halogens. Hydrogens and halogens. For example, if you look here, this is the methane, CH4. If you wanted to write M, then the number of monovalent atoms are 4, because number of monovalent atoms in chemistry are hydrogen and halogens. That's all. Hydrogen and halogens. If I ask you the number of monovalent atoms attached to sulfur, they are 0, because oxygen is not monovalent. Only hydrogen and halogens are monovalent. Oxygen is bivalent. So remember, M is nothing but the number of monovalent atoms attached to central atom. If you want me to make it easy for you, then it is nothing but number of hydrogen atoms, comma, halogen atoms. You must understand. Number of hydrogen atoms or halogen atoms is the number of monovalent atoms that are attached to the central atom. For example, if it is methane, the number of monovalent atoms attached are nothing but hydrogens, which are 4. Suppose if it is CCl4, the number of monovalent atoms attached to the carbon are the number of halogen atoms, that is nothing but 4. Must understand. So it all depends upon finding H. If you can know the value of H, then we can determine hybridization. Now the question is how? Right? But let's stick to the formula first, that I will tell you. But H is half into V plus M minus C plus A, where H is number of hybrid orbitals, V is number of valence electrons in the central atom, that is nothing but group number for your easy understanding. C is cationic charge, A is anionic charge, M is number of hydrogen atoms and number of what? Halogen atoms. You must understand that. Got my point? So let us apply this formula for molecules such that we can have a straight understanding of what the formula is saying. Observe carefully. Look into this. I draw the attention of everyone as I apply the formula by taking examples. So you have this formula, H is equal to half into V plus M minus C plus A. This is the formula. And suppose if you wanted to know, if you know H, suppose by calculating this, if you get H2, or if you get H3, or if you get H4, or if you get H5, or you can get 6, or H7. Let us restrict here till 7, please. By application of this formula, suppose if you get H value to be 2, 3, 4, 5, 6, then we are in a position to judge what? The hybridization that is taking place. For example, if H is 2, it is sp hybridization. Sp. And suppose if it is 3, it is sp2 hybridization. If H is equal to 4, it is basically sp3 hybridization. sp3. If H is equal to 5, it is sp3d hybridization. If it is 6, it is sp3d2 hybridization. If H is equal to 7, then it is sp3d cube hybridization. You must understand. Right? How do we get the values of H 2, 3, 4, 5, 6, 7? Then we have to apply this formula. So once you apply this formula, you will get H values. If you get H values, check in this list. If it is 2, it is sp. If it is 3, it is sp2. If it is 4, it is sp3. If it is 5, it is sp3d. 6, sp3d square. 7, sp3d cube. Right? Now what we will do, we will take a example of a cation of an anion or a simple molecule, and then apply the formula to find out H. Once you know the H, I think you are through the hybridization. Let us understand this. Watch carefully here. Example 1. If you take methane and you wanted to know what is the type of hybridization in carbon in methane, right? Now, if this is the case, let us apply. H is equal to half into V. V is the valence electrons in carbon. So the number of valence electrons in carbon. So every time you cannot write the configuration to count the number of valence electrons. Here I am counting, but we don't do again and again. Look into this. If I can count, the carbon is 6. So it is 1s2, 2s2, 2p2. That is a 6 configuration, and the outermost shell is 2. So I'm underlining this. This is the shell number 2. This is the outermost shell. So in the outermost shell, you have total 4 electrons. So what is V? Total valence electrons. It is difficult for us to every time write the electronic configurations. Normally we don't do this. So better remember the group number. And carbon belongs to 4th group. You must be knowing. Carbon belongs to 4th group. So straight away let it put it. H is equal to half into V is group number of carbon, that is 4th group, plus number of monovalent atoms. M is what? The number of monovalent atoms. When M is number of monovalent atoms, I told you in chemistry the number of monovalent atoms are nothing but hydrogen and halogens. You need to count the number of hydrogens or halogens attached to the central atom. Central atom is that where the hybridization is taking place before bonding, intermixing is taking place. That is carbon here, right? So the number of monovalent atoms are 4. You can see here 4 hydrogens, where M is the number of monovalent atoms, that is nothing but hydrogen and what? Halogens, you must understand, right? So 4 plus again M is also 4. This is finished, this is finished. Now the question is C. What is C? C is a cationic charge. So the charge on a cation. First of all, it is not a cation. You see here, methane doesn't have any charge. It's a neutral molecule. It is not a cation. It is not an anion. It doesn't have a charge. So I put it to be 4 plus 4 minus 0. It is not even an anion. It doesn't have charge. So 4 plus 4 is 8 by 2, that is 4. So what I got here is H is equal to 4. And you can see this list. If H is equal to 4, then it is sp3 hybridization. Then it is sp3 hybridization, you must understand. So in methane, the central atom is basically undergoing sp3 hybridization. So I have judged the hybridization in methane. So let us put the entire draft of formation of methane, because now we are in a position to judge what? Hybridization. So let us do that. Let's go and check out methane. Now methane is fixed to be sp3 hybridization. So why delay? Why delay? The methane structure through hybridization. So I write the draft. Here is the draft. Here is the draft. I have fixed the carbon undergoing sp3 hybridization. It is fixed, right? So if it is not fixed, check it out again. If it is methane, then H is equal to half into, this belongs to 4th group. So it is 4. Number of monovalent atoms are 4. It's not a cation, it's not an anion, so it is 8 by 2, which is 4. If H is 4, it is sp3. It is fixed. So once it is sp3, let us write the draft. Let us start the draft. The draft says, in methane, the central atom, that is carbon. Now what is central atom? Central atom is that where the intermixing is taking place. The intermixing is what? Taking place. You must understand. So in methane, the central atom, carbon, right, undergoes sp3 hybridization. It is sp3 hybridization. Now, students who are listening to me get confused. How do you know? Well, you might be knowing. How do we know? It's sp3. How do we know? Then I gave you a formula, which is H is equal to half into V plus M minus C plus A. You can see here, V is 4. Number of hydrogens attached to that carbon is 4. It's not a cation, it's not an anion. So H value is 4. So naturally H is 4. It is sp3. I gave you the list. So no confusion. It is sp3 hybridization. I know, you know. If you don't know, use the formula. The central atom, carbon, undergoes sp3 hybridization. When it is sp3, well, in sp3 hybridization, then bond angle for sp3 is 109 degrees 28 minutes. It is fixed. Very strange. Still I have not participated in bonding. Still I am only undergoing hybridization. My partner is far away. I am now getting ready in a direction, sit in a direction, structure is fixed. We don't move in that direction. I will call the partner for participating in bonding. So when it is sp3, hybrid orbitals, they are better directional properties. So I am sitting in directions of 109 degrees 28 minutes and the shape is also fixed, that is tetrahedral. Everything is fixed before bonding itself. And I have fixed hybridization also using the formula, right? So if I continue the draft, this is what it is. So in methane, the central atom undergoes carbon, which undergoes sp3 hybridization with bond angles 109 degrees 28 minutes and tetrahedral shape. So if I write the ground state configuration of carbon, the ground state configuration of carbon, which is 6. So if I can write the ground state configuration of carbon, then it is 6. It is like this: 1s2, 2s2, 2px1, 2py1, 2pz0. You can see here. So 6. S has 2 electrons in the outermost shell. And then you have P, you have 2. Right? I have gone singly first using Hund's rule. First you need to be half filled, then only pairing occurs. So you have a 2px1, 2py1 and 2pz vacant. That is in the ground state. Well, remember, it's a common sense. To participate in bonding, you can't do that in ground state. You must get excited. Atoms participate in bonding in excited state, not in ground state. Just like that, you can't participate in bonding. You need to get excited. Now, why are you getting excited? Because in methane, the hydrogens are approaching. When the hydrogens are approaching carbon, they vomit energy. In methane, you have 4 hydrogens. Unless the carbon is excited, you can't participate in bonding. So the hydrogens are approaching the carbon. All the 4 hydrogens have vomited energy. And that vomited energy is eaten by carbon. So if you see here, this carbon eats away H nu. This is energy vomited by hydrogen atoms while approaching what? This carbon. The carbons are approaching. When they approach, when I walk from here to here, I lose energy, right? Similarly, the carbons are approaching what? Sorry, the hydrogens are approaching carbon. They are also vomiting energy. And that vomited energy is eaten away by that carbon. And we were told the difference between a ground state and an excited state is simply a quantum of energy. And the quantum is nothing but h nu in science. Either you eat 1 h nu or 2 h nu or 3 h nu or 10 h nu or 100 h nu. You can't eat half h nu or 3 by 4 h nu. That's Planck's quantum theories. The energy is quantized. So if someone is asking you, when you venture out as a science student, someone is asking you, what is the difference between a ground state atom and an excited state atom? You simply tell him that it's a quantum of energy. And the quantum is denoted by h nu. So let the quantity vomited by these two fellows is nh nu. N packets have been eaten away by the carbon, then it rises to excited state. Then one of the s electrons is kicked toward the pz. So I can write the excited state configuration. The excited state configuration, and the carbon is now in excited state. It is 1s2, one of the s electrons is kicked to p, 2py1, 2pz0, z0 has now become 1. So you have 4 unpaired electrons. 4 unpaired. Well, the hydrogens are approaching fast towards carbon. So I need to be ready for participating in bonding. So I got into excited state. I kicked the s electrons to p. I Now I need to sit in a direction. I need to sit in a direction. I must be sitting in a direction with a bond angle. Then ask the partner to come, we'll have overlapping. Right now I am in excited state. Next what I will do, I will intermix and undergo hybridization. And what type of hybridization? I already mentioned, sp3. So the hydrogen is approaching, I got into excited state, now I'll intermix. And what intermixing it is? sp3, because we have fixed that. Now look into this. Now what happens? Hybridization of 1s and 3p's. 1s and 3p's. I lock it. You have this 1s and 3p's. And the hydrogen is approaching, so what they will do is they will intermix. Intermix and get ready. Get ready means sit in a bond angle of what? 109 degrees, 28 minutes. Then clap and ask the partner to come. I'm ready. Right? So let us intermix. So 1s and 3p's, 1 plus 3 will give you 4 sp3 hybrid orbitals, with bond angles 109 degrees 28 minutes and the shape is tetrahedral. So I'm getting ready, no time. I'm getting ready, the hydrogens are coming, they are vomiting energy, I have eaten, I have risen to excited state. Then for getting ready, I should be sitting in a position. When the hydrogen approaches, then I can't ask the hydrogen to come like this, come like that, come perpendicular, come acute, come obtuse. These things won't work. So I should be ready, right? So what I'm doing is I intermix all these 1s and 3p's and get ready by sitting at a bond angle of 109 degrees 28 minutes and the shape is tetrahedral, which I'm writing now. 4 sp3s. 1, 2, 3 and 4. This is one sp3, this is other sp3, this is other sp3 and this is other sp3. These 4, 1, 2, 3, 4. And total number of electrons involved in hybridization are 4. Count it. 1, 2, 3, 4. And the 4 need to be distributed here. And follow Hund's rule. All the rules applicable to atomic orbitals are applicable for hybrid orbitals, you must understand. So all the 4, if you wanted to fill, you can't fill like this. 1, 2, 3, 4, no. 2 here, no. It should be half filled. Look here. 1, 2, 3 and 4. Now I am ready. I am ready, please. Come. And I am inviting whom? The hydrogen. Come, please. Come and overlap. And here is the overlapping. And this bond is SsP3 because the hydrogen has electron in 1s. So it is S and versus what? sp3. And if it is SsP3, it is sigma bond. It is SsP3 sigma bond, SsP3 sigma bond, SsP3 sigma bond. And here it is the methane molecule. Look into this. This is one sigma, which is formed by SsP3. This is another sigma, which is SsP3. This is another sigma, which is SsP3. This is another sigma, that is SsP3. Look into the shapes of methane molecule, which we explained, right? So look into the sequence of events, what we are doing. First of all, the carbon ground state configuration is this. All the 4 hydrogen atoms are coming towards carbon. They are vomiting energy. And the carbon has eaten away that energy. So it risen to excited state because bonding will happen only in excited state. In ground state, you can't have bonding. You should have that conducive excitedness to participate in bonding. And in the excited state, one of the s electron is kicked to p, and you have 4 unpaired electrons. Now, after excitation, you just can't call the partner, come on, we'll have bonding. No, you must be sitting in a position. Please sit in a position first, because after the hydrogen approaches, then you think about it, come acute, come this way, come that way, all these things are ruled out. You be ready. Be ready in the sense, undergo hybridization. That's where I have done. 1s and 3p's, giving you what? 4 sp3 hybrid orbitals. Bond angle is 109 degrees 28 minutes, and tetrahedral and all this. And once I am ready, then understand that the hydrogens will overlap. So the concept of overlapping is still there. The concept of overlapping is still there. You can see here we are still using the concept of overlapping because we say it is s-sp3 head-on. S-sp3 head-on overlapping. So the concept of overlapping is the thing which you can carry forward in the entire chemistry which you will be pursuing. You must understand. That is one of the biggest merits of Linus Pauling, which you can't discount. So if I can put it properly, the same methane molecule, look here, these are the highlights, right, of methane molecule. Watch carefully here. The case of methane, right? So what are the features of it? First, it will undergo sp3 hybridization. If you wanted to know how, use the formula H is equal to half into V plus M minus C plus A, in which half into 4 plus 4 minus 0 plus 0. So ultimately you will get H is equal to 4, hence it is sp3. Hence it is sp3. You have to fix that first, right? And then once it is fixed, bond angle is 109 degrees 28 minutes. And the shape is tetrahedral. And here it is 1s and 3p's, 4 sp3 hybrid orbitals. Right? So the structure will be looking like this. The tails must be visible. And all the 4 electrons are now ready. And now the S comes, and it is S-sp3 sigma. Similarly, another hydrogen, it is S-sp3 sigma. It is basically S-sp3 sigma. It is S-sp3 sigma. So you have 4 sigma bonds, 1, 1, 2, 4, right? So if I can write the Lewis structure, it is like this. So you have 4 sigma bonds. Bond angle 109 degrees 28 minutes. Shape is tetrahedral. You must understand this. Got my point? So, initially when you wanted to write the draft for hybridization, you should use the formula H is equal to half into V plus M minus C plus A. And then first find out what is the hybridization. After finding out the hybridization, write the ground state configuration. Once you write the ground state configuration, you must be getting into an excited state. Because only in excited state, hybridization will take place. After all, the bonding also takes place in excited state. And in excited state, how do you get into excited state? your partner approaching you, as in the case of hydrogens approaching carbon, they vomit energy, they will be vomiting energy, and that vomited energy is taken away by the carbon, and the central atom rises to excited state. After rising to excited state, it is not straight participating in bonding again. You must be sitting in positions. So you will undergo what? Hybridization. You will be undergoing hybridization. And then once you undergo hybridization, you are sitting in positions. The bond angle is fixed. The bond angle is fixed. The structure is fixed. The shape is fixed. Everything is fixed. Then you ask the hydrogens to come down and we'll have overlapping. So remember, even when I'm discussing hybridization, I'm still not divorcing the word overlapping, because the concept of overlapping introduced by Linus Pauling to explain the strength of the covalent bond continues.